June 26th, 2026. Today, the universe has delivered a message across 13.8 billion years of cosmic time, and a team of physicists in Japan have finally learned how to read it. In a groundbreaking announcement made today by the International Center for Interdisciplinary Science and Education, the Super Kamiokande experiment has, for the first time in history, recorded the diffuse supernova neutrino background, or DSNB, with a statistical significance of 2.6 sigma, a 99.5% confidence level. This is not just a discovery, this is the opening of a new window onto the history of the universe itself. It is the sound of every supernova that has ever exploded, whispering to us across the eons in the ghostly language of neutrinos. And it is happening on a day that also marks the birth of one of the most formidable minds in the history of physics, a man who would have been utterly fascinated by this achievement. Because today, June 26th, is the 202nd birthday of William Thomson, better known to the world as Lord Kelvin. Let me take you back to Belfast in the year 1824. A boy is born into a world that is just beginning to wake up to the power of science. His name is William Thomson, and he is a prodigy of almost incomprehensible magnitude. By the age of 10, he is enrolled at the University of Glasgow. By the age of 12, he is winning prizes for translating Latin dialogues. By the time he is in his early 20s, he is already challenging the scientific establishment, writing papers under a pseudonym to defend the radical new mathematics of Fourier against the conservative British physicists who were still living in the shadow of Newton. This was a man who, from the very beginning, was not content to accept the received wisdom. He wanted to understand the fundamental laws that governed the universe. And he did, in ways that still shape our world today. Lord Kelvin is a colossus in the history of physics. His contributions are so vast, so foundational, that it is almost impossible to imagine modern science without them. He formulated the first and second laws of thermodynamics, the laws that govern energy, heat, and the irreversible arrow of time. He established the absolute temperature scale, the Kelvin scale, which is the bedrock of all thermodynamic measurement. He developed the mathematical analysis of electricity and magnetism, laying the groundwork for Maxwell's equations. He made fundamental contributions to hydrodynamics, to the theory of elasticity, to the physics of the Earth's age and its shape. He even played a pivotal role in the laying of the first transatlantic telegraph cable, solving the complex physics of signal transmission over thousands of miles of ocean. He was, in every sense, a giant. But Lord Kelvin was also famously, spectacularly wrong about something. And that wrongness, that beautiful human fallibility, is one of the most important lessons in the history of science. In the late 19th century, Kelvin calculated the age of the Earth based on its rate of cooling from an initially molten state. He came up with an estimate of somewhere between 20 million and 100 million years. He was off by a factor of about 50. He did not know about radioactivity, the internal heat source that keeps the Earth's core molten and extends its age by billions of years. And when the evidence for a much older Earth became undeniable, Kelvin, to his great credit, admitted he was wrong. He accepted the new evidence and moved on. That is the mark of a true scientist. Not infallibility, but the courage to change your mind when the data demands it. This brings us back to today, June 26, 2026, and the extraordinary announcement from Super Kamiokande. The experiment, a vast underground detector in Japan, contains 50,000 tons of ultra-pure water lined with thousands of sensitive light detectors. It is designed to catch the faintest flashes of light produced when neutrinos, the ghostliest of all particles, interact with the water molecules. Neutrinos are almost massless, they carry no electric charge, and they interact with matter so weakly that trillions of them pass through your body every second without you ever noticing. They are produced in staggering numbers by nuclear reactions in the sun, in nuclear reactors, and in the most violent explosions in the universe, supernovae. When a massive star, at least 8 times the mass of our sun, reaches the end of its life and its core collapses, it releases an unfathomable amount of energy. About 99% of that energy is carried away not by light, not by the expanding shock wave, but by a burst of neutrinos. These neutrinos stream out of the dying star, carrying with them the story of the collapse, the story of the creation of heavy elements like carbon, oxygen, silicon, and iron, the very elements that make up our planet and our bodies. Since the universe began, supernovae have been occurring constantly. The neutrinos from all these explosions, from the very first stars to the ones that died just moments ago, have been traveling through space, accumulating into a diffuse, ever-present background, a cosmic neutrino fog. This is the diffuse supernova neutrino background, or DSNB. It is a fossil record of stellar death, a history of the universe written in the most elusive particles known to science. Detecting this background has been one of the holy grails of particle physics and astrophysics for decades. The signal is incredibly weak, buried under a mountain of background noise from other neutrino sources. But Super Kamiokande has been pursuing this goal for years. The team analyzed observational data spanning approximately 5,000 days, combining two phases of the experiment, a period using ultrapure water alone and a later phase where gadolinium salt was dissolved in the water to enhance the detection of the neutron signature that accompanies a neutrino interaction. And today, they announced success. They have detected the DSNB with a significance of 2.6 sigma. That means there is only a 0.5% chance that the signal is a random fluctuation. It is not yet the gold standard of 5 sigma, the level required for a formal discovery in particle physics, but it is a profoundly significant result. It is the first time anyone has seen the diffuse supernova neutrino background. It is the first time we have directly observed the cumulative neutrino glow of every supernova that has ever occurred. It is, as the scientists involved have said, a key scientific goal that has been pursued for many years. Imagine what this means. Every second, somewhere in the observable universe, a star is dying in a cataclysmic explosion. The neutrinos from that explosion travel across the cosmos, unimpeded by dust, by gas, by magnetic fields, by anything. They travel for millions, for billions of years. And then a tiny fraction of them, an infinitesimal fraction, pass through the 50,000 tons of water in a mine in Japan and produce a faint flash of Cherenkov light. That flash is captured by the detectors, analyzed, and interpreted. And in that flash, we are reading the history of the universe. We are seeing the death of stars that existed before the Earth was formed. We are seeing the nucleosynthesis of the elements that made life possible. We are seeing the universe in a way that no telescope has ever seen it before. And it is happening on Lord Kelvin's birthday. There is a beautiful symmetry to this. Kelvin, who wrestled with the age of the Earth and the fundamental laws of thermodynamics, would have been captivated by the idea of a diffuse supernova neutrino background. He was a man who was fascinated by the deep history of the cosmos, by the processes that shaped our planet and our existence. He would have understood, perhaps better than anyone, the significance of this achievement. He would have seen it as a validation of the scientific method, of the power of curiosity and persistence to reveal the hidden workings of the universe. And he would have been the first to point out that this discovery, as momentous as it is just the beginning. The 2.6 sigma signal is a tantalizing glimpse. It is a confirmation that the DSNB is real, that it is there, waiting to be studied in detail. But to truly unlock its secrets, to use it as a tool to understand the history of star formation, the rate of supernovae, the nucleosynthesis of heavy elements, we need more data. We need larger detectors, more sensitive instruments, longer observation times. We need to push the significance to 5 sigma and beyond. And that, as Kelvin would have appreciated, is the nature of science. It is a slow, patient, cumulative process. Each discovery opens up new questions. Each answer reveals a deeper mystery. This brings me to another anniversary that falls on June 26th. In 1985, on this very day, the German physicist Klaus von Klitzing was awarded the Nobel Prize in Physics for his discovery of the quantum Hall effect. The quantum Hall effect is a phenomenon that occurs in two-dimensional electron systems subjected to low temperatures and strong magnetic fields. Under these conditions, the Hall resistance, the transverse voltage divided by the current, becomes quantized, taking on discrete values that are universal, independent of the material, and dependent only on fundamental constants of nature. It is a stunning example of quantum mechanics at work on a macroscopic scale, and it is a discovery that has revolutionized our understanding of condensed matter physics, leading to the development of new quantum standards of resistance and playing a key role in the definition of the kilogram and other SI units. Von Klitzing's discovery is a reminder that the universe is full of hidden symmetries and beautiful patterns that emerge when we push matter to its extremes. So on this day, June 26, 2026, we have 3 threads to weave together. We have the birthday of Lord Kelvin, the father of thermodynamics, the man who gave us the absolute temperature scale, the man who was brilliantly right about so much and humbly wrong about so little. We have the announcement from Super Kamiokande, the first detection of the diffuse supernova neutrino background, a cosmic symphony of stellar death. And we have the anniversary of the Nobel Prize for the quantum Hall effect, a discovery that revealed the quantized nature of electron behavior in 2 dimensions. These three threads are not separate. They are connected by the deepest currents of physics. Thermodynamics, the study of heat and energy, is the foundation upon which our understanding of stars and supernovae is built. The quantum Hall effect is a manifestation of the quantum nature of matter, the same quantum nature that governs the interactions of neutrinos. And the detection of the DSNB is a triumph of experimental physics, a testament to the power of human ingenuity to build instruments that can capture the faintest whispers of the cosmos. It is a story of how we have learned to see the invisible, to hear the inaudible, to touch the untouchable. It is a story that Kelvin would have loved. Let me leave you with a thought. Kelvin once said, "If you cannot measure it, you cannot improve it." It is a statement of the fundamental importance of measurement in science. But it is also a statement of humility. It acknowledges that our knowledge is limited by our ability to observe. The detection of the DSNB is a profound expansion of our ability to measure the universe. We are now able to measure the cumulative neutrino output of all supernovae that have ever occurred. We are able to measure the history of star formation and death on a cosmic scale. We are able to test our models of stellar evolution and nucleosynthesis with a new independent probe. This is not just a measurement, it is a new sense, a new way of perceiving the cosmos, and it is a reminder that the universe is still full of secrets, still full of things that we cannot yet measure. The diffuse supernova neutrino background is now within our grasp. But what about the cosmic neutrino background from the Big Bang itself? That is still undetected. What about the nature of dark matter? What about the unification of quantum mechanics and gravity? These are the next frontiers. These are the challenges that await the next generation of physicists, the ones who will build on the legacy of Kelvin and von Klitzing and the Super Kamiokande team. So tonight, as you look up at the stars, think about the neutrinos that are passing through your body at this very moment. Some of them were born in the heart of a star that died billions of years ago. Some of them were born in a supernova that exploded in a distant galaxy just a few hundred years ago. They have traveled across the universe unimpeded to reach you. They carry with them the story of their birth, the story of the elements that make up your body, the story of the universe itself. And now, for the first time, we are beginning to read that story. We are beginning to understand the diffuse supernova neutrino background. It is a story that Lord Kelvin, with his profound curiosity about the age and nature of the Earth, would have been desperate to hear. It is a story that Klaus von Klitzing, with his exploration of the quantum realm, would have recognized as a profound manifestation of the underlying order of nature. And it is a story that we, the curious ones, the ones who refuse to stop asking questions, are privileged to witness. Stay curious. The universe is speaking, and we are finally learning to listen.